So we'll have a record. Last week in my, I guess what I have, 8 classes, I missed 2 with starting the recording. That was a little bit of, um, let me check here, participants. This group might want to hear the chime when people come in. We'll see. Yeah, this is different. I get to look into your homes a bit if you don't have it set up, and got my dog outside. She's been out about 3 minutes. I don't want to let her out too long. She seemed to be feeling kind of sick today. Okay, so how am I on the grading? Well, I actually did mark a few of the exams. If things go really well, I'll have everything graded by the midterms. If they don't, I'll make a reasonable guess based on stuff. But I'm pretty sure I'll have exam done, and I'll certainly count you as having submitted homework if you have. So we'll we'll look into that. There are some people who haven't submitted anything yet. Gets a little hard to assign a good grade in that situation, but we'll see how things look. We'll maybe get to the slides and look at the attendance. Participants, there's 12, and maybe I can I take the attendance with split screen? Why don't I share my PowerPoint, and can I now am I sharing the PowerPoint? You are screen sharing. I'll stop the share, and what should I share? Share my screen, so you'll see what's on the screen, and the PowerPoint's there, and I guess I can see a window of here, and maybe mark the attendance. And I have a drawing tool that I can use. Let's see. Who's here? There's about 12 of us here, and I see 9. Is it going to let me drag this down? Okay, I see 12. And go to the PowerPoint. And Joe Blackcrow, is he there? Kimmy Mila, is she there? Felicia's there, so we can mark her as attending. And Ryan, is he there? No. Jermaine is there. Terry Haskell, I don't see Terry. Eleanor, I don't see Eleanor. Janice, Joelle Janice. Probably some people that get those names misordered. I'm probably not the first, right? And is Brad here yet? Not yet. Let's see. We can go. What?
Brad's here.
Brad's here. Oh, okay. Sorry, I forgot forgot the top of your head there. uh, uh, Brad Keckler, and then we can go down. Let's see. Tamara King is here. Somebody dropped out. Tiff. Megan's here. And Christina's here. Oh, so Joni's here. Christina Payne is here. Tawi, Tawny, Victoria Phelps is here. Okay. One of the Victorias. And
It's Victoria Phelps.
right. I see the name. Is Brittany here? I thought I Samantha. Samantha has that really great makeup done in the photograph. Usually don't see students with such great makeup. And let's see, Sherry, haven't seen her in a while. Justice is here. Justice is here. And Shah is here. Okay. Yeah, this seems to work. Somebody, oh, go back. Tony is there. Tony is there. Justice. Hopefully you guys can see this. I don't know what you're actually. I didn't ask what kind of devices you're on. Yeah, it's a lot easier with a laptop. We had I guess we had kind of a Zoom party on a Saturday night. My wife's cousin died. Oh, I guess going on 2 weeks ago. It was either Wednesday night or Thursday morning. Yeah, it was kind of strange. He was sleeping in a truck stop, and overnight he passed. So so it was Wednesday night or Thursday morning. And what and we were sort of meeting online for some prayers, and at the end of those on Saturday night, we all decided to sort of eat at the same time. Oh, Joseph can mark you here. We all decided to eat at the same time and be online, and so my wife's an immigrant, and she's got family all over, and I guess her brother was from the Philippines. She had another brother in Calgary, a sister in Phoenix. Um, um, her cousin's wife and daughter in Chicago. My daughter in New York. Me in Rapid. My son and his family in Colorado Springs. So it was really a big kind of international Zoom party. Uh, that's really really strange. So yeah. Oh, and my wife had a cousin and his at least one of his daughters in Bahrain. So everybody's just all all over the world uh, and doing Zoom. Um, that's uh, yeah. So some people were eating breakfast, and some folks were having dinner, and uh, like the Philippines is like 14 hours ahead of us, so it's, um, it was different. So I think having everybody, Felicia, usually she's around.
I'm
Yeah,
here.
yeah, okay. I didn't mark you yet. I'll do that. Uh, see, Ryan, no, Terry, Eleanor, some people we haven't seen too much of. Need to maybe uh, Tamara King, but not Tiffany. Uh, Christina Payne, Townie, Victoria Phillips, but not Victoria. Brittany, not yet. Samantha. Samantha must have. Oh, there she. Yeah, Samantha with the. Uh, and then Justice and Shaw. Okay. Um, well, maybe I can. What can I do? Uh, I can maybe stop the share. Stop the share. That might be the thing to do. And then go to make the PowerPoint large. Take up the whole screen and collapse that and get back to my screen. All right, I think I got the attendance up. And oh, I probably should get the dog back in. So I'll cut out and we are recording. And maybe we can we'll we'll resume the recording. So we're back. Um yeah, uh, maybe I should try to get get a cute graphic to put up for my login picture. Uh, we'll see. Uh, oh, and maybe we've been playing with the PowerPoint, and I tried to mark it up and look at the names this time. So I'm kind of learning to do this stuff, right? So now we can just share the PowerPoint and share, and you are screen sharing. Let me. Did I get the right share down? Let me share PowerPoint, not screen, and share. Okay, and uh, oh yeah, I've got this. Uh, and minimize. All right, and slideshow. Um, maybe from the beginning. Yeah. Okay. Um, so chapter 8 we'll look at this time. Just a somewhat straightforward test step from before. We had our first hypothesis test, and it turns out we can um, come up with hypothesis tests for all kinds of things. And we just want to clean up one of the situations here. And this is the one sample t-test when sigma. So this is when sigma is unknown. Um, we last week we looked at the case we might call it a z-test when we test means against a standard or assumed value. And but we assumed we knew sigma, um, the standard deviation. So we did know the standard deviation, and uh, that's um, that's. But this time, in a common practice, when we take a sample, we frequently don't know it, and it's a slightly different case, and you have to make some adjustments for it. And this is the t-test. Uh, uh, and we talked through the attendance. I used a different tool. That's why it's not marked as cleanly as it usually is, but that's okay. Uh, no, that was a mistake. Kimmy, uh, Kimmy isn't here, so I don't. Uh, oh, uh, let's go to the pointer and um, let's see. Control P. Uh, mistake. Okay. Well, now we can go forward, I think. Um, maybe Tiffany will show, maybe Victoria Pena will show, maybe Brittany will show. Um, and haven't seen Sherry in a while. I'll have to look into that. Oh, I guess there's one thing it would help me if you submitted your assignments something like this. Uh, your files, last name, uh, first name, maybe an underscore, first name, chapter, or whatever, um, and then whatever you care to hear, dot doc or something, or dot PDF. Um, so Checha and Bowen, uh, one sample t-test when sigma is known. Uh, let's see. I guess there's a relatively curious question about the t-test that we can mention, and maybe I can stop the share when we story to tell. Uh, eh, I'll wait on that. Um, so this is it. What you know, we did the z-test before, and generally a hypothesis test disease, and sigma was known. We assumed it known, um, and then we could test mean, our sample mean versus a standard, and that's kind of nice thought there. In z-test, we just assume that we know the standard error. In reality, sigma is mostly unknown. Okay, when it's unknown, we calculate an S, and uh, E, uh, is it the best estimate of sigma? There's actually some, and what do I have here? Do I have my, yeah, I should get Control L. Um, there is some some theoretical statistics books have a technical definition of best, and it isn't quite the best. It doesn't quite meet those standards, but um, yeah, for the purpose, it's really a nice estimator of sigma. So we call this sigma, we call this S. We do the sample standard deviation, and we do the um, and we can run through and uh, S is usually smaller than its biased estimator. It's usually smaller than sigma. The sample variance S squared is an unbiased estimator of the population variance sigma squared. And this is just remember what the S squared formula is. Degrees of freedom, this is almost always, n minus 1. We call this SS. Um, and yeah, it was on your final exam, to find SS. What do we mean by unbiased and biased? Um, what we mean is on a long-term average value of S squared, it's going to work out to sigma squared. So theoretical average of S squared works out to sigma squared. Because of taking the square root, um, the theoretical average value of S doesn't work out to be um, value of sigma. And showing you how to get those theoretical averages kind of assumes you've had a calculus class. And at this point, um, it's more trouble than it's worth. Um, so, and talk about this. I don't believe I'm going to ask any question about bias and unbiased estimators. It's kind of nice to know. But exactly what that means is probably not worth sharing. One sample T statistic, estimated standard deviation of the mean, S sub x bar is calculated. So this way we get this formula, and we then get T is equal to x bar. What? X bar minus mu. Okay. Over S. And this is the comparison value, the theoretical value, and this is the observed value. And this is S over the square root of N. So that's estimated standard error, standard of the mean. Oh, this is certainly a mistake here. Standard error. Okay, maybe I'll have to change that sometime. Yeah. So it looks very similar. The um, Control L. The T statistic looks very much like the Z statistic for the Z test. Just same numerator, and we literally just replace sigma with S. And we talk about with degrees of freedom n minus 1. And this T value doesn't have a standard normal distribution, so we need a different table, a T table. might be before we get started talking about tea, maybe we can stop the share a bit, and I can look at some of you or some of your pictures. um, there's kind of an interesting story about the tea statistic. Um, one very dedicated a statistician first developed the first set of tea tables, and um, we might have somebody guess, and this is kind of a trick question. His name was William Seeley Gossett, and he worked for a, company that was known for producing a certain class of beverages. What kind of beverages was it? Does anybody know? Anybody want to guess for the tea distribution? Nobody wants to try the.
Dr.
Oh,
Pepper.
Dr. Pepper? No, it wasn't Dr. Pepper for the tea distribution. I haven't had that answer tomorrow, but
It was just a guess.
it's fine. It's I was thinking somebody might have thought tea. I don't know. Haven't went down and toured that Celestial Seasonings facility in Boulder or anything. Talk about tea. Uh, I haven't uh, I haven't been there. My my son and daughter-in-law have toured Celestial Seasonings in I guess it's near Boulder in Colorado. Anyway, you but no, um, William C. Lee Gossett worked for Guinness, and he was making beer. So uh, so kind of a cute problem. You would think a tea distribution would be about tea, but uh, his company wouldn't let him publish under his name, trying to keep secrets about how they did things and what they were working on. So he referred to himself as student. So it's a student's tea distribution. Um, uh, will uh, um, so yeah, and to develop the oh, it's a long story. He took a year off of work to gather data, and he gathered the data by uh, going to prisons and measuring people's index fingers. I think that's actually probably illegal now, but or the legality is kind of a question. So gathering data is something you might want to think about. So that's the one of the stories about uh, Gossett. Actually, working on statistics is kind of worthwhile. He ended up running the company for a while and was on the National Barley Council there in the United Kingdom. So was it Ireland? I don't remember. Anyway, so maybe we can go back and share again. So a little side story of share that screen. Well, when conducting a t-test, the calculated t needs to be compared to a critical t-value. It sets the boundaries of the rejection zone. The only difference is one, the z-curve, but the specified t-curve differs for every degree of freedom. So as our sample size changes, we get a different distribution, and that that makes it, and they're indexed with this thing called degrees of freedom n-1. And why they didn't index it with just the observations in the one sample, I do not know for sure, but that is the common practice. Variations are noticeable, except especially for small samples with n is less than 30. So many books will say, let's stop the share and see who's arrived. Anybody? Just wanted to see who's arrived.
It was me, Frank, Joni.
Okay, you're back.
But I got kicked out because I lost service, but I'm back.
Oh, okay. So I marked you in. All right. Sounds good. We'll share again. No, attendance is a big thing. OLC. So we've got different, and we get a different kind of table. We just get tables of the boundary zones, usually for the t distribution. You can get if you have Excel or Google Sheets, there are functions in there that will allow you to calculate more common kinds of values and let you fill out, for example, for each degree of freedom, a separate T table that looks like our Z tables. However, we don't. Would be kind of an interesting assignment, but that'd be for a different time. Yeah, this kind of picture usually shows up in the T curves with 5 different degrees of freedom, and the highest peak is the blue peak with degrees of freedom equals infinity, the Z curve. So the highest peak here is this Z curve, and it slides down, and if you can follow it, it also is the flattest on the edges. And the one with the longest tails, the heaviest tails on the end, is with the fewest degrees of freedom. And what those values are, we probably can get it out of the book. Figure 8.1. Okay. And degrees of freedom, infinity. The curves are degrees of freedom 1, 2, 3, and 5. Yeah, actually, that degrees of freedom 1 has some cute properties, and we the textbook shows it essentially. The tails get heavy as the degrees of freedom increase. The tails get lighter and the peaks get higher with the T distribution. I didn't look up a video for that. It certainly might be kind of fun to find one. I would certainly guess somebody's done that. have somewhat a summary for the t-test. T-tests are especially developed to conduct comparisons with means and population means, particularly when the sample size is small and sigma is unknown. So we need that. Sigma is unknown and S is used as the best estimate of sigma. And maybe it is important to use the degrees of freedom n-1 from the table to calculate the sample variance and sample standard deviation. Okay, the degrees of freedom for the sample t-test is n-1. There is a unique t-distribution for every degree of freedom. So that's so summary. We have t, and we have to come up with a formula for S. If you put the t-test formula and the z-test formula together, you can see they're nearly the same. We just replace sigma, a given value, with S, a calculated value. So not much of a difference there. The t distribution table. The t table provides critical values of t that set the boundaries of the rejection zone for t-tests given three pieces of information: one-tailed or two, degrees of freedom, and alpha level. The shape of the t tables is the t curves are symmetric. It's appropriate to conduct t-tests when the population is normally distributed or when the sample size is large and greater than 30. All right, so we should supposedly check for normality. We're kind of assuming it with a t-test. We are assuming it with a t-test. However, it's hard to actually, with small numbers of data, be able to reject the normality assumption. Yeah. So here's a portion of the t-table. And one-tailed alpha level, two-tailed alpha level, and we can look up numbers on this page. And this is right following in the back of your book where the Z table is. So instead of like 496, it's 497 and 498. And I built a table that looks something like this in Excel. I stop the share and share my T-table efforts. Oh, wrong share. Stop share. Share. And this one. Okay. And I probably should have opened the whole thing. Yeah, and view zoom 200%. Looks a bit like what's in the book, so close enough, right? Close enough for showing things. It doesn't look like it's a photograph, but can stop the share and bounce back and look at this. Colors aren't exactly right. The markings are a little different. Anyway, can work with that. So we've talked about this. We probably should work through some examples. Four-step hypothesis testing procedures still recommended for a t-test. The t-table lists both the one-tailed alpha and two-tailed alpha. You simply have to identify the column with the correct alpha level. Alpha over 2 becomes a symbol for the two-tailed test with alpha level instead of a calculation. There are only positive t-values reported in the t-table. Negative t-values can be identified by adding a negative sign to the reported value. So we only get the positive values. And here's an example done. Oh, I didn't, I have my last spring's rather, comments about the words we chose for hypothesis tests. And we said usual and strange last time for the alternative, for the null and the alternative hypothesis. And I didn't update them from for this year's words that we picked. And I don't remember actually what they were. Sometimes you go and work through your slides and don't always update things or think of how to update. So ACT composite scores are normally distributed with mu is equal to 21. A sample of 25 students is taken randomly selected from a local high school with X bar is equal to 23 and S is equal to 5.2. So we're given those numbers. Does the data support the claim that the average ACT composite score of the students at this high school is higher than 21 using alpha is equal to 0.05? So we state the key word here is higher. This is a right tail test. So our usual situation, our null hypothesis, our H0 is mu is equal to 21. And this is something the ACT will tell you. And H1, the alternative hypothesis is the greater than. It's a right tail test, and this is the strange or changed situation. Identify the rejection zone. 3 pieces are here. Right tail test, alpha is equal to 0.05 degrees of freedom, n minus 1 is equal to 24. And the critical value for this is 17.1. The rejection zone then is 17.11. And probably, do they show the t-table? No. I've got a t-table. I can stop the share and bounce out and look at my t-table. So it's a one-tail test. I guess this should have been white. It's a one-tail test. So we look at this row and we have our degrees of freedom, 0.05. So this column, and then because of our alpha level and it's a one-tail test, it's the 0.05 value here, alpha one-tailed. So we're looking down this column F, and then we have to go all the way down to 24. And I didn't use that kind of pivot, those freeze panes commands on this table. We can go down to 24 and Oh, here's the A is the degrees of freedom. 24, 29 is just the role in the Excel table. So across this way for the 24 and up this way for the um, alpha is equal to 0.05 and right-tailed, and the 17.11. So this is the degrees of freedom column, the A. So we have to go down this column all the way to 24 and go along this column here and read across from the 24. And that's how you get to that. And back to sharing the PowerPoint. I just talked through where that 17.11 came from in the table in the back of your book, just following the Z table. So it begins on 497 and ends on 498. So not too big a long table. Calculate the test statistic, and that's just a matter of crunching the number out. And we get 1.93. So compare 1.923 with the rejection zone. T is greater than F. T follows. Therefore, we reject the usual consideration and at alpha is and there's strong evidence to support the claim that the average ACT score at students from this high school is higher than 21. So high school looks, and we're getting towards 6 o'clock. Hypothesis tests using and what do we have? Another example. We have 9 students. Assume that the reaction time for seeing a green light and pushing a button is normally distributed with mu is equal to 220 milliseconds. And some of you who now the book's written by a psychologist, and these are sometimes the kind of games psychologists play in labs. Sometimes they do more dangerous things, but this is the kind of game. It's important to know how quickly people can react to it's a green light and how fast you do it. If it's a red light and you're driving, how quickly a person could commonly react. And the millisecond is a thousandth of a second. So this is roughly, a fifth of a second. On average, people react. So we have 9 student athletes, and they would guess their reaction times might be a little faster, depending on what they do. Well, I mean, if somebody plays baseball and is a shortstop or a catcher, you might assume that they really have great quick reaction times. But other student athletes, if somebody's in track and field and is a thrower, throws a shot put or a javelin or something, maybe they don't have to react as quickly. So, student athletes do differ quite a bit. Um, Not to say that uh, people who are throwers in track and field don't have to train and become dedicated to their sport or things, but there isn't the idea that they have to react very quickly. If they are a tenth of a second slower than someone else, walking up and starting, it usually isn't a problem. So, do the student athletes differ from? So, differ means two-sided. Using alpha is equal to 0.10. So, state the hypothesis. U is equal to our usual case, our null hypothesis, our H sub 0 mu is equal to 220. And our unusual or strange situation is mu is equal to, is not equal to. So this is a two-tail test, and alpha is equal to 0.10, and degrees of freedom is n minus 1 is 8, and the rejection zone, therefore, is t, the absolute value of t is greater than 1.86. And we can probably pick that off my table again. So I'll pop up the table and see if we can get to I know how to get to the 1.86. So there we are. It's a two-tail test, and it's 0.05. So actually, that's column F again, right? So we're going to be in this column, but we have 8 degrees of freedom. So this row, this column F, this row 13, and we then get the 1.860. And that's like I said, these functions are in Excel, and you can calculate them. And so I didn't like type this whole table in or scan it or anything like that. I just used some of the functions in Excel and let it run the calculations to fill the table. So there might be last decimal difference between one table or another. This one likely works out exactly the same, right? Uh, uh, there's a different, oh, uh, it's a different, oh, in my textbook, they actually have the blue and white. So two-tail test, 10 and 8. Okay, my book has 0.86 with no 0, and my a computer program in Excel shows the 0. Not a big difference. It's just um, um, how I did the Excel. I just probably could make it look that use the print layout that the other system has. So share then back to the PowerPoint show. I see why Maggie just copies the whole screen and bouncing back and forth and stopping shares instead of just displaying stuff. So our rejection zone here is T greater than 1.86 or 1.860 if you looked in my table. And well, we have to calculate the test statistic. We have X. We can sum the X's and get the 17.37, and then divide by 9, 1.93, 193, and then okay, I'm gonna stop the share and see who's arrived. Brittany, you just arrived?
Yeah, I just got off work, so I just got on.
Okay, I'll pop back and get you marked for the attendance.
Okay, thank you.
Okay. And at least that will see if we can pop way back to the beginning. Whoa. Right. All right. I guess now that I'm here and most of us are here, last week, I guess 2 weeks ago, I didn't announce it and I didn't send an email, and classes weren't actually available. But what I did was we did have class and there weren't that many people there. However, the class was recorded, and to make up for the class missing it, you can watch the video and answer the question I have in the email. So you can just watch into the video, and towards as actually there are two videos because I forgot to put the record on. You you can answer that question and I'll mark you as attending. Now also if you submit the homework from last week, I can mark you as attending too. So but it's a whole lot easier to just answer that one question to verify that you'd watched at least part of the video from last week to get marked as attending. So we have to hold a class session for every scheduled class, and I probably the week before we should have tried to schedule a makeup time or decided that we would run the class. So guess we can skip forward. Calculate the test statistic, and now x minus x bar and square it, and we have this. And oh yes, you would like to have some machine do this for you, right? And you come up with a number, and that's your SS quantity. And here's the formulas in different ways, the way the author likes to show it. It's not the way I like to write it. I kind of like to write this and then this in the denominator. And so we have all of this, and our standard deviation is 78.4 milliseconds, and our mean is 193 milliseconds. And let's see, do the athletes differ? Minus 1.03. Is the t-value? No, the absolute value of 0.103 is not there. So the calculated T does not fall into the rejection zone. So different athletes might have different reaction times. So we fail to reject H naught, our usual situation, and the athletes don't appear. These 9 athletes don't appear to have greater reaction times, and I don't know if we were more careful about which sport we looked at or motivated the people well. For example, baseball players might have quicker reaction time than golfers or shot putters.
And Frank,
People, yeah.
the PowerPoint isn't on the screen.
Oh, okay. I'll I'll escape. Yeah, I do, and go back to the Zoom, and I can share PowerPoint. And okay, I'm sharing now, and a slideshow from current slide. Where did we stop? We were on this screen. You've seen this screen already, right? We bounced out, and laser pointer did the calculations, worked down. When we came up, we calculated the S, we were given the mu, calculated the X bar, the N were given, and computed T is equal to minus 1.03. But the absolute value of T is not greater than 1.86. So it doesn't fall in the rejection zone. So we fail to reject H0. And we conclude for this set of 9 athletes that there isn't much of a difference, that they don't differ from the standard with this set of 9. And I guess we would look at differences, what kind of sport they are, and what, if they're a thrower in track and field, they may not work at having better reaction times, or if they're a golfer, don't often have to react. In other sports, basketball, football, baseball, people, tennis, have to have it's an advantage to be able to react more quickly.
Mom. Supper is ready, please. Mom. What? Oh my gosh. Yeah.
Okay. Extra example of the t-test. An article in the Journal of the American Medical Association examined whether the true mean body temperature of 98.6 degrees Fahrenheit. So this is something you've learned to come about. Average body temperature is 98.6, and you decide to conduct your own study and take the temperatures of 25 participants, and yeah, there are different methods of doing this. Those of us who in this COVID times, I remember going into a couple different doctor's offices, and just put a little sensor on your forehead to uh, read your temperature and being asked questions and how are you feeling. And one of them was in one of my appointments was like in June, and I said I have some hay fever symptoms, and scared the person that I had watery eyes or something, and uh, it's just no, you don't need a COVID test if you think you've got hay fever symptoms. I hope not. And you find the mean is 98.25 and with a standard deviation of 17.3. Evaluate the claim. So well, let's see. Control P. Our null hypothesis, our usual setting, our H sub 0, mu is equal to something. And what is that something? Somebody want to guess? We've got only, 4 numbers on the board? Well, 5.
98.6.
98.6, great. Just what we're hoping for. And our H1, our alternative, our strange case is what?
25.
What's that? This one's kind of subtle because it's a little hard to say what's going to happen. This is a not equal to or two-sided test because we're
98.
evaluating 98.6. Yeah. Okay, so we've stated the two hypotheses. That's kind of easy. And calculate the rejection zone. Identify the rejection zone. So it's two-sided. So our t statistic, absolute value will have to be greater than something, and this is n. So our degrees of freedom, df, is equal to what? N minus 1. And that's equal to 24. And so two-sided alpha is equal to 0.05. And we can go look at the table and stop the share. We'll start a new share with the t table. And it was alpha is equal to 0.05, two-sided, and 24 degrees of freedom. So alpha, it's two-sided, alpha is equal to 0.05 for this G column here, which it's two-tailed, alpha is equal to 0.05. And then we have to go down this column here for 24, and I probably should do a freeze panes on this thing. If I can remember how to do those. Go down to 24, and so this row for 24, this column G for alpha is equal to 0.05, and 2.06. 2.06 is what we want, that number. So stop share, share PowerPoint, share. And this then 2.06. Oh, okay. So we'll have to go through and do our calculation step. Calculate the test statistic. T is equal to, this is the formula, X bar minus mu over S divided by square root of N. Okay, so I have to get the numbers in here first. Ask if you can identify those. So what number goes here for X bar?
$25.
25 is N.
0.05.
0.05 is alpha, and it doesn't go into the equation directly. So another number up there, I want to guess. X bar is the sample mean.
98.25.
Great. 98.25. And mu is equal to what?
73 degrees, or 0.73 degrees.
Mu is this. Let's see.
98.6.
98.6. Yeah, our assumed value from way back. And the S. Only a few numbers left up. What would that be? That's the 0.073. Do some of the calculations. Some are a little easier than others. So this is then negative 0.35 for the numerator. Know if that's what you've got. The 0.73 is there, and divided the square root of 25. I don't know, when I was in school they made me memorize these, so yeah, 5 is what we have. And might want to try to grab a calculator and do that. And I don't know, I guess I got a calculator in my phone, and I'll try to crunch out that number. And maybe the phone isn't the best thing because it's only got about 18% battery life. My old phone's probably got an old phone that's got 38%. It's got a tools calculator. Let's see. 0.73 divided by 5 equals
Is it negative 107?
You get negative 107.
1.072
1.072.
is what
See if,
I get.
let's see what I get. Or I'll wait for somebody else to tell me. Um, Let me try that again. Clear. Uh, 7.5.
Would you do that bottom part first?
You could.
I got negative 2.397260274.
Okay, so I negative 2.397, and don't have to get all excited about carrying it. So one suggestion. And another. Now we probably should let some people go and think about this a little and crunch your numbers again, because we got a little disagreement. And there are a couple of different ways to do this. The way I usually do it is this whole thing, because we're dividing by a fraction in the denominator, is the same as 5 times negative 0.350 divided by 0.73. So that's another way to do the calculation. So checking that 0.35 divided by 0.73, and I get just a little less than 0.5 times 5, and I ended up getting this value here.
Yeah, I checked my numbers too, Frank, and I miscalculated one number, so I came up with the second one as Brad did.
Okay, sounds good. So anybody disagree with this number? Okay, so I think we've got some agreement. Minus 2.397, and we can so that's our t value. We calculated that and make the correct conclusion. Well, t is equal to negative 2 and what was that? 397. And our rejection zone is t greater than, and was pretty modest number if I remember that, 2.06. 2.06. So our t is in the rejection zone. So our T is in the rejection zone. And maybe I don't like this and. So our T is in the rejection zone. Therefore, we reject H naught, our usual assumption. H naught, our usual, our null hypothesis. And claim that the average temperature is different than 98.6 degrees F. Okay, so that's interesting. Well, it's kind of a labby kind of thing. No, not really a social science kind of problem. There's another way of looking at this problem. Confidence intervals is kind of a debate. Somebody left. They dropped a line, I guess. Defined as an interval of values calculated from sample statistics to estimate the values of a population parameter. So we can. So this is the idea. Provide additional information on which to base a researcher's conclusions. Lets us know how precisely we're working. Does not require a hypothesis about the population mean. Can be appropriately applied when the population is normally distributed and when the sample size is larger than 30. 2 steps of constructing the confidence interval is we get the point estimate. That's usually for the T confidence intervals, it'll be the average. The interval estimate, we often get the margin of error that we talk about. A point estimate is a single value of the sample used to estimate a population parameter. A sample mean is used to estimate the population mean. Okay, the single value does not tell us the quality of the estimate. Therefore, statisticians extend the point estimate to an interval estimate. Let me pause. I want to pause the recording. Want to check. All right. So this is the game, and this is the philosophical discussion. Chat. Okay. See you, Joni. Okay. I guess I got a private chat, and the student gave an excuse why they left. Okay. And that's the default. If you do directly to one person, is it's private. So I I I shouldn't read those out loud. Okay. So the single value does not tell us therefore we have an interval estimate, right? Okay. The interval estimate, as the term suggests, refers to a range of values used to estimate the population parameter. The width of the interval estimate depends on the confidence level, 1 minus alpha, and the confidence level 1 minus alpha percent confidence interval. So it's very often T alpha over 2. Alpha over 2 is simply the subscript to identify the critical T value for two-tailed test at the alpha level. So that's a subscript notation. But what it means, use the two-tailed column and let alpha and use the appropriate alpha to get the T there. And we use this term margin of error, E. And these also come in other types of statistics. So if you listen to political discussions, you know, I don't know, um, you know, something on PBS like Washington Week or Meet the Press, or I don't know, something on MSNBC or Fox News or CNN. And they talk about surveys, they talk about margin of error, and estimates of percentages. And sometimes these are phone estimates, and people make phone calls and ask questions of, you know, are you a likely voter? And if so, who are you going to vote for? And um, and it depends if you ask 1,000 people or 2,000 people, the margin of error varies a little. A lot of times people want to try to make those phone calls to like 1,500 people, though, to get the margin of error is pretty common. Somebody new returning, drop line or something. Okay. So that's nothing real special, that alpha over 2. So it's alpha. It really means just alpha. Look at the two-sided column for the purposes of this class. You have upper and lower confidence intervals. So this is the upper limit, this is the lower limit. And a lot of books usually, maybe I should go back and see if somebody's new is showing up, so I can stop the share. And somebody new, Brittany, did I mark you as attending? Brittany's still connecting. I guess I can go back and check. Don't remember all these things. Breaks up the dull stuff, right? Yeah, okay. See if we just popped in. This probably looks strange on the video. all these clicking
Oh.
slides.
That was me. This is Brittany. That was me. I just switched from my laptop to my phone.
Okay. Okay. So that's the formula. This is the upper limit. This is the lower limit. And the notation, this plus minus, just means this. We sort of combine the two formulas together and put the plus minus there. So the CI or confidence interval is this. So if you see this, well, plus minus, what does that mean? It means this is one limit and that's the other limit. Let's compare CI for the two-tailed test. Going back and looking at the reaction time model, we had the reaction time problem. We had no, there's a mistake there, right? Yeah, we go back and look at that reaction time. Problem. The mean was 193, not 93. So so there's a mistake here.
You have to share your screen again.
Oh, okay. I'm sorry. It's, keep and go back to my Zoom and Zoom meeting, and I should share this. Go back to the PowerPoint, and that was the mistake I was just talking about. The 193 lost the character, and we've got the share going on, and I now can get back to the slideshow from current slide. All right. And same calculations we had previously for the standard deviation. And we then, degrees of freedom is 8, two-tailed test. Our t-value for t alpha over 2 is 1.86. So this is t alpha over 2. And it'd probably be helpful to do this. Just note that. This is t alpha over 2. Okay. Not just the next thing we write there, I guess. All right, and then we do this little calculation. T alpha 2 is equal to 4.86, and this is then the margin of error is 48.6. We can write this way and then add and subtract, and we have then our bracket, our 90% confidence interval is this in the lower and upper bound. Just round to one more decimal than the original data. Yeah. So this is the recommendation. Obviously, when you do the calculations, the decimals can carry out quite a bit, but this is the reporting convention of the book. Getting to 6:45. Interpretations. The correct way to interpret a 90% confidence interval, that we're 90% confident that the population for all student athletes, the mean will bracket that. Okay. So 90% CI includes the population mean, and mu is equal to 220. So what happens is when the population, when the confidence interval covers the population mean, it's equivalent to saying a two-sided test fails. So same sort of thing happens, and in other classes, it's done as kind of a formality. But we show it formally, but we won't here. So an outcome from a 90% confidence interval is consistent with the two-tailed hypothesis testing of fail to reject. So that's interpretation of that. Let's see. Got a chat message. Oh, okay. All right. So, okay, I got a private message, and probably should go back and get the attendance again. Well, let me pop back. All right. Okay, so got you marked in, Tiff. Now I have another problem. Campus newspaper reported the average hours of sleep for students at a neighboring university is 6.5. This has made you curious about the amount of sleep students get at your university. You randomly selected 4 students on your campus, and the amounts of sleep are 5, 3, 6, and 2. I I don't know where you get those sleep totals, but I've got a Fitbit device, and it tells me how it will measure my sleep if I look on my phone, but don't have that. What is the estimated hours of sleep for this population, and what's a 90% CI? So that's the question we have, and that doesn't look like too hard a calculation. So maybe we can go through that example. Whoa. Well, I guess I didn't leave that many slides left. So we'll need the mean, and we'll need the standard deviation. So mean X bar is equal to 5 plus 3 plus 6 plus 2 over n, which is 4. And then that's 8, and 8 is 16 over 4 is equal to 4. All right. And the standard deviation, S squared, we might want to look at, and erase that. We'll look at the sample variance first. That's the summation of x minus x bar squared over n minus 1. And let's hope they give us a nice number here. They could. 4 minus 1. And then x. So 5 minus 4 squared plus 3 minus 4 squared plus 6 minus 4 squared plus 2 minus 4 squared. Well, that then is equal to, let's see, 5 minus 1, 5 minus 4 is 1, squared is 1, plus 3 minus 4 is negative 1, squared is positive 1, plus 6 minus 4 is 2, squared is 4, plus 2 minus 4 is negative 2, squared is 4, and this then is 3, and so this then is 10 over 3, or 3.33 onward, right? 10 over 3 is s squared. And then, so we'll need to take the square root of that. S is equal to square root of s squared. And no, I'll have to grab a calculator for that one.
Are you squaring up 3.333? Is that what we're doing here?
We'll take the square root of that.
That's what I meant.
Okay. All right. I'll clear square root. And right, works out to be 1.8 to, meant to write it to 1.826 is S. So our formula then is for our confidence intervals, oh, I had two pages there for that. What was our formula? Our margin of error is T alpha over square root of n. Okay. So margin of error, T alpha over 2 S divided by square root of n. We need to look up, we have degrees of freedom. Degrees of freedom is equal to n minus 1. Therefore, when we look up the T, we can stop the share and share our T table. And oh, what was that? What was our alpha value? 95% confidence interval. Says alpha is equal to point. Oh, okay. So alpha is equal to 0.05. All right. Need to escape, keep, and then Zoom. I can share my T table. Alpha is equal to 0.05 and share. I should freeze the panes on this. Alpha is equal to 0.05 and it's two-tailed. So this is the column we look at, column G. And we have 3 degrees of freedom here. So read across there and read down here, and we get 3.182. Okay, 3.182, and we can stop the share and go back and share PowerPoint and 3.182. That's what it was, right? Before I share that, let me verify that again. 3.182. It's been kind of a long day. Share PowerPoint. Share slideshow from current slide. There, we're back. All of that to 3.182 times 1.826 divided by the square root of 4, which is just 2. And then we can multiply that out. Let me see what I get. Uh, 2.905 is our margin of error, 2.905. So a 95% confidence interval is 4 plus or minus 2.905, or bracketed 1 point 6.905.
Say something.
A 95% confidence interval is
Something close to the screen.
4.925, or the bracketed value here. So it works out to just what we had at 7. Let me go and check on something here. Stop the share. Somebody's okay. All right. Just clean up some of that background noise. Oh, still got that screen. Go back and share that. So that's the last example I wanted to talk through today. And where are we? Okay. We did the attendance. I didn't do the tech check. I did that early on. OLC it actually gotten a lot of resources to have people get set up on that. Now as the COVID things are getting more difficult, yeah, I don't know if you guys are getting locked down anywhere or not. Some discussion on that. We talked about the students' T distribution, and I guess the question is, for some of the people who came up late, there's a story about that other books will say the students' T distribution, and then give a story about William Seeley Gossett, who's famous for putting together the first T tables, and it took a lot of work. So there's a T distribution. And then there are hypothesis tests using t-tests. So we used the hypothesis test in the t-table, and I showed you my t-table, and I probably should add a freeze panes feature on it. We talked about confidence intervals, and we did a couple of extra examples. And believe I have to submit the midterm grades on Thursday, and I have actually started grading, but I haven't reported or returned anything yet. We'll see how that works out, and I think I've got about a half hour extra to answer some questions or whatever, so I can stop the share if we like. Somebody's got some questions about whatever, I can answer that in a private chat window or a discussion here. No, I haven't been so great about getting back to email. I owe Tawny an email. I did get back to Joni. She had to leave though. Okay, so ready to call it done for tonight? No?
Sounds good to me.
Sounds good to Brad?
Well, I had a couple of questions, so but if they want to go, that's fine. But
Okay, I can hang around a bit.
so my question is on chapter 6.
Chapter 6, okay.
Yeah.
See if I can answer something from chapter 6. Okay. Question from chapter 6. Gotcha.
I'm stuck on those last three, that 11, 12, and 13. I kind of have my numbers figured out for 12, but putting the puzzle together.
11, 12, and 13.
Yeah.
Okay. We have Z values that 99, the middle 99% apart from the rest of the distribution. So let's see, middle 99%. What are the Z Z values for that? Maybe I'll share a whiteboard and draw. Got a whiteboard and have a group here, and this is 99% in the center. So it's symmetric. So this side then is 0.050, and this side is 0.050. All right, so this is then a negative Z value, and it's here. So we can read center. So we have a to the left of table. So read 0.050 from the center of the table. To the edge. Okay, so we can stop this share, and I can share then and this is the T table, but I also have a Z table, and that's the positive numbers, and this is the negative number side, and we can bounce upward. Uh, Zoom in. Oh, I zoom. That's a little big. 200%. That's 400%. That's a little bit big. So we have the negative side, and we're looking for 0.050 in this table here to get our result. 0.050 is close to this, and turns out it's right between these two numbers here. Okay. Um, oh wait, no, that would give us a 90%. I'm sorry. I'll stop my share, and I'll go back to sharing that whiteboard. They got the wrong number there, so whoa, what they do? I'll get my eraser and erase that. I made a mistake. I put the wrong number in, and I'll get back to my drawing tool, and it's 0.050. Okay, for 99%. And I need to erase this to get that correct and draw. And so that's the number we'll look for from the table. So we can stop this share and then share the table. And we'll look for 0.00 0.005. Looks like we're finding that number about, these two are the closest, 0.258, negative 2.58, and negative 2.57. So it would be one of these two numbers, and it's negative 2.5, and we read up from this column here. So do we have one of those answers in the book? Yeah, so it's answer D. Read. So we can stop the share and share. Read. Z is equal to negative 2.58 or so. And then, answer D. Okay. So got that one answered for you then?
Yes, thank you.
Okay. Mm,
Then, like I said, on number 12, I got my sigma and my X bar and my mu, but
Okay.
there's a A and a B. Am I supposed to answer both of those, or?
For number 12,
Yep.
is that the problem in the book, or was that one of my
It's
additional problems?
it's the free response question
12,
12.
and there's an A and a B in
No,
your
because it's what am I doing here? There was two ways that I had written them down there, that I have written down, one as A and one as B. That's so I didn't know because
what is the probability?
Go ahead.
Okay. Yeah, so well you just have to give one number a probability.
What
and
is the
there's
probability that the water taxi overloads when carrying 15?
yeah.
Okay. Sigma. So I use that as my, okay, put my 15 here. Okay. Alright. And then on number 13, it just wants how I'm going to solve that. That's the way I take that question.
What is
Maybe
the
I'm wrong.
probability that the sample mean of this randomly selected 16 online to get an insurance quote is longer than 17 minutes? No, they want a probability. So on
Okay.
that last question, what is the probability? Is so there's a number they want, a probability.
Alrighty, then I'm also almost done with chapter 7 there too, but the next thing is I don't know how I'm gonna get these to you because I'm on quarantine now.
Okay.
Today my mother tested positive, so according to the protocol where I work, if I'm exposed to someone who's positive, I'm on a 14-day quarantine.
Okay. Well, you can send me an email explaining your situation. I don't know exactly your circumstances, but I mean, you could write something out, take a picture with your phone, and maybe upload it. I don't know how good you are with those kinds of things, but
Not too good.
okay.
But I could
Okay.
try to get something figured out.
Yeah, I don't know exactly what equipment you've got. So, all right. Send an email explaining your situation. Certainly take that into account, that you can't like get into the office like you normally would.
Yeah, because before what I was doing was scanning them in to my email, and then I was able to upload and save on my jump drive and like that. Or either
Okay.
or go to the college center and do the same thing, but now I'm on quarantine. I can't leave my house. So, but I'll
Okay.
get something figured out and I'll do an email to you in regards to our conversation here.
Okay, sounds good.
All right.
All right.
Okay,
So,
Frank.
okay, I can stop the share and see if anybody's still around.
Nope.
Just you, Jermaine. We call it done?
Yes.
Okay.
All right.
Right,
Take
I'll
care.
stop the recording. All right.